what we are trying to do is we are trying to understand how a circuit works, but basically by answering a couple of questions. What is the role of the battery in a circuit? And when a current flows through a circuit because of the battery, then what happens if there is a device that has been put there, some component like a bulb or an LED, let's say. And the basic thing is that when you put a battery, we know that electricity, for a charge to flow, there has to be 2 points, one with a higher electric potential and one with a lower electric potential. And the analogy is that of, you can think of it in terms of water tanks. I've already said this before, but basically if you have a water tank which is higher and a water tank which is lower, and you have water in the higher one, if you pour water into the higher one, then there is going to be a flow of water into the lower tank. So basically, because there is a difference in potential between these two water tanks, the water will flow until, of course, it attains some kind of an equilibrium. Okay, and naturally, if you want the water to continuously flow, then you will have to create uh, you have to keep the difference in potential, in this case gravitational potential, going by continuously adding water. So you have to spend energy for that. So the battery in the circuit also does exactly the same job. What it does is it maintains a potential difference of, let's say, 1.5 volts. And we have to sort of decipher that a little bit. I think we have discussed that before. When you say 1.5 volts, what you really mean is that this battery is maintaining a difference of 1.5 joules per coulomb between the positive and the negative terminal. Okay, so if you again see, every point of time that when I talk about a unit like this or explain a unit in this manner and you don't really get it, go back to thinking in terms of the definition of what is potential, electric potential and potential difference. Okay, so that's, and I'm repeating it for the nth time, and I'll do it very briefly, don't worry. um, you have to understand that when you move a charge, what should I use? I'll try to use, okay, some kind of a neutral. Okay, when you move a charge from one point to another, this positive test charge, blah, 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 then it has a potential at this point, it has a potential at this point, and you have to do work to get it from, let's say, position A to position B. I know I have changed this A and B many times. Sometimes this is A and this is B, and sometimes this is A and this is B, doesn't matter. But basically, there is a difference in potential between these 2 points. So the battery is the one that's actually doing the work in creating the higher potential, okay, continuously. So it goes from here to here, and then the battery puts it back. It goes from here to here, and then the battery puts it back, and so on and so forth. Oh, sorry, it's the other way around, isn't it? It will go from here to here, and then the battery puts it back. Here to here, and then the battery puts it back. So think in terms of that to understand this. So 1.5 joules per coulomb is the amount of energy the battery is putting per coulomb, and therefore it is maintaining it at that level. Now, how the battery maintains that, you don't need to worry too much about that. All you need to say is that it's converting chemical energy into electrical energy. Okay, so inside a battery, there is a energy change that is from chemical to electrical. If you are interested, if anybody is interested in how exactly a battery does that, you can look it up. There are plenty of information available on the internet on how a battery works. If you get a sense of that also, it will be very useful. But for the rest of us, it's enough to know that it just maintains a potential difference. So basically what happens is that the water keeps getting filled over here. That's the idea. Okay, so therefore, and the one other point is that there is no backflow possible. So just like there is no possibility of water flowing from here to that side, the battery also maintains some kind of an internal barrier so that the electricity doesn't flow within it, in case that is a question for any of you. If it is not, then that's fine. Again, it's a point that I have repeated several times, so I won't labor it anymore. Now, having said that, we come to another situation. So this is the next situation. We want to understand what exactly happens when the charge, say, starts flowing through the battery and then the bulb lights up. And in order to understand that, we can look at a situation in which there is no bulb in the system, okay, in the circuit. So you just hook up a battery like this. You just connect it through a copper wire, the positive terminal to the negative terminal, and allow whatever to happen. So then I ask the question, what is the difference between these two circuits? Let us sort of put it as circuit A and circuit B. All right. And what Kian told me was that when you do that in circuit B, there is a current that is flowing through the circuit. And that's like the water flowing through it. There's a potential difference. You have connected the two tanks, so the water is going to flow. And that's what is going to be happening over here. The water is going to flow. And now when you look at a circuit, you kind of forget about this analogy of the water flowing, okay? Because if you keep thinking, there's a tendency to keep thinking about the analogy to understand what is happening. The analogy stops here, okay? So don't look at the analogy anymore. Think in terms of flow of charges, maintaining of potential difference, and in terms of electricity. So when a current flows through this circuit over here, you can say that some charge is flowing per second through any point that you look at. Remember, I kind of uh, drew another analogy for understanding that, which is that you go to any one point in the circuit and you kind of imagine yourself sitting on a rock and counting the number of electrons flowing through this point, okay? And when you do that, you get, let's say that you're able to, at the atomic scale, just for the heck of it, count the number of electrons that are flowing through. Then you will be able to see, because each electron has a particular amount of charge, you will be able to say how many coulombs are flowing per second. So basically you've become what is known as an ammeter. Okay, and we have to look at the working of an ammeter also a little bit later. I'll introduce the idea of that, but this is the hint. The ammeter is able to, in some way, count the number of charges flowing through any given point in a circuit per second. Okay, so you are the ammeter in that sense. So you get the value in terms of coulombs per second, and I have told you that the unit of coulombs per second is also abbreviated to ampere. Okay, so if you have a current of 1 coulomb per second, then you have a current of 1 ampere. So from here onwards, we will be talking in terms of amperes of current, and it is abbreviated to capital A. So the symbol for current is I. The symbol for the unit of current is capital A. Okay, both capital. So then I asked, what is happening in circuit A then at the same time? And of course, the observation is that in the circuit A also, there is going to be a current. So there is current flowing between the positive terminal and the negative terminal of the battery. That is just by convention. So then what is the difference between these two, apart from the obvious fact that there is a bulb here and there isn't a bulb here? So now we have to start thinking, and any inputs will be welcome. I hope the whole thing up to now is clear. If anything is not clear, please ask. Otherwise, let's explore further. So to just bring back the question again, what we are basically trying to answer is, how does the bulb work? Okay, what happens in the bulb that makes it glow? We don't know that yet, but what we know is there is a current, and we are kind of comparing two situations, one in which there is no bulb in the circuit and one in which there is a bulb in the circuit. So now it's time for theories. So if you put out 2 or 3 theories, then we can examine those theories and we can see which one seems to be fitting our sort of situation the best. So yes, don't all shout at once, but let's start putting out our theories. Okay, so just to sort of talk about some of the responses. one of the responses made by Rudra was that in the bulb, the difference between these two circuits is in the bulb, there is a conversion from electrical energy to light energy. And that conversion is not going to take place in the other circuit, in the B circuit, because there is no bulb over there. And then somebody else Ishan wanted to look a little more closely at the bulb and say what is happening at the bulb. So at the bulb, we kind of figured out that what is going to happen is that there is going to be a current through the bulb itself. And the bulb happens to have a filament, a tungsten filament. And that tungsten filament, when current passes through it, it becomes hot. It becomes so hot that it starts emitting light. Okay, and that is how a basic incandescent bulb works. Most of the time we use LEDs. LEDs don't quite work in the same way. But let's look at the simpler situation of the incandescent bulb. And then we came to the question, if you you imagining yourself as the ammeter who is counting the number of electrons or charge flowing through per second, what if you looked at the filament? What would you see? Okay, so Ishan says, well, you would see charge flowing through, obviously, because the bulb is lighting up, there is energy conversion taking place. But he also said that the charge would slow down a little bit. Okay, and that's where a kind of classical mechanics analogy does not work with electricity. That's one of the places, because um, there is a contradiction over here, and I would like to explore that contradiction a little bit more. So if you observe at this point, let us say at this point, and you saw that there is a certain amount of a certain amperes of current flowing through. Okay, and you looked at this point. Okay, uh, again you're being the ammeter, so you're looking through that point, and I think I'll start drawing the amperes symbol over there. Okay, so you are the ammeter, right? So there is one ammeter here and there's one ammeter over here. uh, would there be what would you observe here at this point?
It would be pretty much the same
as
as the first point.
as the first point, and why do you say that?
Because after the resistance near the bulb will start accelerating again.
Again, where were you, Aristotle? I mean, why would it accelerate after the bulb?
I mean, because it's going to the potential, lower potential, whatever.
Okay, see, that's the reason why I said that you forget about the hydrostatics analogy, sorry, hydrodynamics analogy at this point of time, because electricity behaves in a completely different way. There is no way you can know this without me having told you or you having studied it earlier. So I'll introduce a concept. Okay, you have heard of the law of conservation of mass, the law of conservation of energy, the law of conservation of momentum. There is a law of conservation of charge also. Okay, so you cannot increase or decrease the charge that is available. That means you cannot produce charge out of nothing. Okay, so if there is a certain amount of charge that is flowing through a circuit, that amount of charge has to be the same everywhere in the circuit. Otherwise, there is a decreasing or increasing amount of charge, and that will violate that fundamental law. Okay, that charge cannot be created or added to. I don't know how the statement goes, but I'll just stick to this statement: the charge cannot be increased or decreased. So if charge cannot be increased or decreased, then how do you explain what is happening at the how do you explain what you think is happening at the filament, that the charge is slowing down? Why will the charge slow down? Have I made my question clear? Is it clear what I'm asking? Because as I was talking, I myself was not clear if I was clear. But what I'm stating is law of conservation of charge. You're saying that the amount of charge will be the same at both these points, but Ishan is saying the charge is going to slow down at the bulb. So why Ishan is saying it's going to slow down at the bulb is because he's saying, well, the charge is losing some energy. So if it is losing some energy, then it has to, that energy has to come from somewhere. So it's tempting to conclude that what is happening is that the kinetic energy of the charge is reducing. Okay. So now I throw another googly at you, is that the charge itself does not move very fast through a circuit. I think I've made this statement earlier, but it bears repeating. There is a flow rate of charge. Okay, and you might think that charge flows at, at or nearly at the speed of light through a circuit, because electrical signals also move at that speed, almost at the speed of light. But actually the charge itself in a circuit can do something like about 5 to 10 centimeters per second. Okay, and that flow rate is excuse me, some people are still celebrating Diwali here. That flow rate does not change as a result of the charge flowing through the bulb. Okay, so it's not the kinetic energy of the charge, and it's kind of ridiculous if you think about it, because the mass of this charge, particularly the electron, one of the smallest subatomic particles that we know of, is going to be ridiculously low, right? So the kinetic energy that you can obtain from even billions of those charges flowing through cannot amount to much. Okay, so it is the energy conversion that is taking place in a battery has not got much to do with the kinetic energy of the charges. Okay, so that is the reason why there is going to be no difference in the amperes of the current flowing through any part of the circuit. Okay, so now we are back to the same position, which is that and by the way, you can also come to the same conclusion by measuring the current in this device. If you measure the current in this device at any point, you will find that the current flowing through any one of these points is going to be exactly the same as the current flowing through these points, provided of course the battery and the wires and all that are identical, more or less. It won't be exactly true in terms of actual physical experimentation. If any of you happens to have components at home, ammeters or a multimeter and so on, you can try this. I don't think we have sufficient time to sort of go into the next part of it, which is we still are hanging with the question, then where does the energy for lighting the bulb come from? So we will come to that in the next class. This class, I'd just like to briefly introduce something that uh, Vinayak sir told me. He tried some project with students during the vacation, his students during the vacation, and he came across something that is very interesting. In fact, he just told me yesterday, and I looked into it just today morning. I'll just share very briefly what he has showed me, and then we will see if we can utilize that further. So this is it's a website called tinkercad.com, and in Tinkercad what you can do is you can simulate different things. I think they have 2-3 different kind of simulators, one for mechanics, and there is one for electricity. So I'm showing you the one with electricity, and there are some sort of interesting things. So basically what there is you got a sort of central pane in which you look at the circuit that you are going to make, and then on the right side on this pane you've got different components that you use in a circuit. Okay, um, and then you can sort of play around with this. You can change the components. Unfortunately they don't have a An ordinary bulb, they only have an LED, so there's no sort of incandescent bulb in the circuit, in the whole thing. And now what you can do with this is you can sort of replace components. So okay, wait, the first thing is that you can start a simulation. So here you have, look at the different components. There is a battery. It's connected by a wire to a LED. And the LED is connected again to the positive side of the battery, but not directly through a resistor. Okay, we haven't yet come to the concept of resistors, but you can get an intuitive idea of what a resistor does. Say, for example, oh no, okay, let me show the first thing. Start simulation. So when you start the simulation, what you see is that the bulb has lit up now. Okay, you say big deal. It's as simple as that. All right, fine. Stop the simulation. Now I want to figure out like what is the role of the resistor over here. Why do I need a resistor? Because in all our circuits so far, all we have done is connected the battery to the LED. So I'm going to remove the resistor over there, and I'm going to connect the battery directly to the LED. Okay. So those who know electric circuits, you can tell me what's going to happen now if I start the simulation. Any idea? There was a resistor, and with the resistor, the bulb worked, the LED worked. I removed the resistor, now I connected it directly to the battery. What will happen? The bulb will glow brighter, LED will glow brighter. That's what you think, right? If there is a resistor and it glowed a certain way, you remove the resistor, it should glow even brighter.
It will burn out?
It will burn out, that's another possibility. Why would it burn out?
Maybe because the resistor, it like keeps the circuit in control, it keeps the current flow in control, and I don't know, it's a LED.
Yeah. So it's like the LED, like let's say a bridge can handle only a certain amount of people walking across it or a certain amount of cars moving across it. If the number of cars going across it increases beyond a certain value, then the bridge is likely to collapse. Okay. So again, a kind of a world analogy, but it sort of works the same way. So you see, if I start the simulation now, it works. It still works. Okay. That's strange. I didn't expect that to happen. I thought I had done something earlier which did not work. So sorry, which worked and now it's not working. What I had done. So let's see if we can understand this a little better. Give me a couple of more minutes, okay? And of course, those who would like to leave now can leave. I put a 1.5 volt battery instead of the coin battery. Okay, and I start the simulation. Nothing. Okay, and then I realized that when I looked at the coin battery was a 3 volt battery. Okay, so the voltage is not sufficient for the LED to work. So then I figured that I can put two 1.5 volt batteries. Okay, and in this case, I'll remove this connection. I'll join these two and join this to this. Okay, and now if I start the simulation, that's what happened. The LED sort of blew out. And then I put back the resistor. And then the bulb worked again. When the resistor was not there, the bulb blew up. Then I went on the LED, and the LED says current through the LED is 136 milliampere, while the absolute maximum that the LED can handle is 20 milliampere. Okay, so if you think about it, that kind of tells us what the resistor does. Um, and I think you can draw a connection between what happened in this circuit, in this simulation, as against what we were trying to examine in terms of the working of the bulb. So I would like to encourage you people to sort of go to this website tinkercad.com and fiddle around with this a little bit. And in the next class we will complete that discussion about how the bulb lights up and how a circuit works. So until then, see you.